Assalamualaikum and good day everyone. Today, I will be presenting the spectral analysis of a metal complex based on the journal titled Comprehensive Investigation on Fabrication, Spectral Characterization and Biological Importance of Cobalt and Nickel Heteroleptic Complex. In coordination chemistry, the UV visible spectrum is a powerful tool to understand the electronic structure of transition metals. According to crystal field theory, when ligands bind to a metal, they cause the d orbitals to split. In an octahedral field, they split into T2G and EG levels. The absorption of light that we see in the spectrum is actually the energy required to promote an electron between these split orbitals, known as DD transitions. In this study, our focus is specifically on the nickel complex, which is a D8 system in an octahedral environment. Such complex typically show 3 spin-allowed DD transitions in the UV spectrum, corresponding to electronic excitation from the ground state to higher energy triplet states. Now, let's look at the figure, which shows the UV visible spectrum of the nickel complex. The spectrum shows 2 distant regions. Below 350 nanometer, we see very intense peaks. There are charge transfer bands, which are high-energy electronic movements between the metal and the ligands. However, the most interesting part for our study is in the visible region, between 400 to 700 nanometer. Here, we see specific peaks and shoulders that represent the DD transitions. The pattern of these peaks confirm that our nickel ion is in an octahedral coordination environment. Next, to analyze the spectrum, we first need to determine the electronic configuration of the metal ion. Our central metal is nickel, with atomic number 28. In its neutral state, nickel has the configuration Ar3D8 4s2. However, in this heteroleptic complex, nickel exists in a +2 oxidation state, since electrons are always removed from the 4s orbital first during ionization. We are left with a configuration of Ar3D8 4s0. Therefore, we are dealing with a D8 system, which means there are 8 electrons in the d orbitals. To be continued, we perform a microstate analysis for this D8 system. Using the combination formula, we calculate a total of 45 possible microstates. By organizing these microstates into a table based on their total orbital and spin angular momentum, we can derive the free ion term symbols. And if you look here, the term generated for D8 are first 3F, second 3P, third 1G, 1D, and 1S. According to Hans' rule, the term with the highest multiplicity and highest L value is the ground state. Therefore, 3F is our ground state term. This is crucial because our electronic transitions will start from the ground state. Finally, we assign the transitions by referring to the Tanabe-Sugano diagram for D8 in an octahedral field. In this environment, the 3F ground state splits, with 3A2G becoming the lowest energy level or ground state. Looking at our experimental spectrum in figure nickel complex, we can clearly see the characteristic features of a nickel complex. Although the D8 system theoretically show 3 spin-allowed transitions, we focus on the 2 visible in this range. The first visible peak, located at approximately 600 nanometer, is assigned to the transition from the ground state 3A2G to the excited state 3T1GF. The second, higher energy peak or shoulder observed around 400 nanometer, is assigned to the transition from 3A2G to the 3T1GP state. The third transition, B1, usually occurs in the near-infrared region and is not shown here. These assignments perfectly match the theoretical prediction for a D8 nickel complex, providing strong evidence that our heteroleptic complex adopts a stable octahedral geometry. Thank you for your attention. Bye!